Okay, مرحبا. Salam. Uh, Today is term 2, week 4, physics AMS, physics CA. Uh, yeah, it's about the terminal velocity and about the elongation. Yeah, they're pretty easy صراحة. Start. Question 1. What affect air resistance? What are the factors that affect air resistance? Obviously the surface area and the shape. So like surface area you can see from like مثلا the parachute. It's like something like this, and then you have the person over here. Okay. uh, the surface area of the parachute is like really high. That's why there's going to be more air resistance. And also for the shape of the object, if like if you guys see racing cars, the way they're shaped, like let me show you race car. Okay. If you look at how they're shaped, not these, obviously these ones يعني هدول يعني these ones. If you look at how they're shaped, the shape is in a way where the air won't really hit the car. It's gonna flow along the car, and it's gonna يعني minimize the air resistance, if you know what I mean. That's why the shape affects it. And obviously the relative speed. If the object is going really quickly, then there's gonna be more air resistance, and if it's going slowly, there's not gonna be that much air resistance. Okay, now this one's about Hooke's law. Okay, look, نحن in physics, when you have a spring, this is a spring. Okay, uh, when you pull the spring down, it's gonna elongate, right? Elongate يعني is gonna stretch. Okay, let me one second. Okay, so this would be the simulation for Hooke's law. Hooke's law states that the way they wrote it is tension divided by delta L equals K. Okay, T would be the force acting. Okay, the force acting. Delta L would be L final minus L initial. Okay, T would be, we said, the force, equals K. K is a constant. It's called the spring constant. Okay, the spring constant, or sometimes you can say stiffness. Okay, in the book they say stiffness also. So L final minus L initial. L is length. Okay, length. So whenever we say final minus initial, you can just say delta L, and this represents the elongation. Okay, so مثلا we have the simulation over here. Okay, we have a spring, and we have the, what do you call it? We have the we're putting it with a force. Okay, so let's say the spring constant is 100. Okay, uh, and the applied force, we can change the applied force. Okay, please remember, before I continue, note that the length has to be in meters always. It has to always be in meters. Okay, if it's in centimeters, you get a wrong answer. Okay, so let's say we want to find how much it's gonna travel, how much the distance is gonna be. Okay, so since we know delta L, since we sorry, to find delta L, if we have this formula, T over delta L equals K, delta L would be T over K, right? The force divided by K. So they gave us that the spring constant is 100, so let's say 100. And let's say I apply it now with a force of 1 Newton. Okay, 1 divided by 100 is 0.01, and it's going to be meters. So let's test it out. Let's add 1 Newton. And is it correct? Yes, it is 0.01 meters. So let's say I change this force now to 100 meters. It becomes 100 divided by K, which is the spring constant, 100. Let's put it 100 all the way. It's going to be 100 divided by 100, which is 1, and here it is 1 meter. So this is just to show you, how the simulation works. Okay, so a non-deformed spring, in question 2, is 15 centimeters long. When a 2 Newton force is applied to it, its length becomes 19 centimeters. Okay, the spring constant. So they want the K. Okay, how do you find K? K is T over delta L, right? The force here, T, is going to be 2 Newtons. Okay, and delta L would be L final minus L initial. So the final is 19 minus the initial is 15. Okay, you get 2 over 4, which is... Oh, wait, I made a mistake. The distances they gave you are in centimeters, yeah? Okay, and I told you it has to always be in meters. It has to always be in meters. So 15 centimeters, if you change it to meter, by the way, from centimeters to meters, you divide by 100. Okay, this becomes 0.15, and this becomes 0.19. Okay, So it's gonna be 0.19 minus 0.15, and you get 2 over 0.04. I think 0.04. Okay, and then you divide this, you get 50. You get 50. Okay, 50 newtons per meter. Okay, question 3. Yeah, the moon, it's orbiting the Earth. What force is responsible for the moon's circular motion? Obviously, gravity. And what can be said about the direction of this force? It's perpendicular to the moon's orbit. This one, just memorize it, صراحة. Yeah, the circular motion. Oh, yeah. So it's whenever you have a circle, uh, it's gonna be perpendicular to the شو اسمه. It's gonna be perpendicular. So like if you draw it like this, the force is gonna be like this, which is, if you draw the normal, by the way, it's gonna be, hold up. If you draw it like this, it's gonna be perpendicular. It's a bad drawing, but whatever. You get my point. Whenever you have a circular motion, it's perpendicular. Um, okay, terminal velocity. Terminal velocity. Okay, let's say you throw a ball. Okay, you throw a ball until you're standing here. Okay, this is you. Okay, you take this ball and you throw it up in the air. Okay, the ball is gonna, once you throw it, is gonna accelerate, right? It's gonna accelerate until it reaches a certain velocity, and that's what we call the terminal velocity. Okay, over here, let's say مثلا over here it stays at, see here it became 5, here it's accelerated 7, 8, and here it became 9. Okay, at 9 مثلا it's gonna, for example يعني, it's gonna stop. No, it's not gonna stop. It's gonna stop accelerating and it's just gonna continue at 9 until obviously it falls back down, right? See, that velocity, that end velocity, is what we call the terminal velocity. Okay, what's important to know about the terminal velocity? It's constant. Okay, and obviously it's related to air resistance, and it's the velocity acquired when the net force becomes 0. At that instant where the velocity isn't changing, that means the net force became 0. Question 5. Racing car bodies have shapes in order to reduce air resistance, and I showed you this. I know these shapes. Question 6. When a material goes back to its original shape after the force is removed, the material is said to be elastic. Yeah, I mean elastic. No, this one you memorize it, صراحة. This one, and there's a question here. This one. Okay, these ones you just memorize them. You memorize these. Okay. I can't really explain them. You memorize each one. Now, question 6. Okay. Yeah. With Hooke's law, since we had the T or delta K, I mean T over delta L, yeah, equals K, right? So that means T and L are directly proportional. So you could say T is over here, okay, and delta L is over here, okay? Since the direct proportion is going to be a straight line passing through the origin, okay? Until, until there's going to be a point where you keep on pulling the string, and then over here, let's say, at 15 newtons, okay, T is in newtons, at over here at 15 newtons, خلاص the string broke. So what's gonna happen? It's gonna keep on extending, obviously, but it's gonna extend like this now. Okay, so it was going up straight, then خلاص it breaks. Okay, so it changes the course. So that's where you call, that's what we call the elastic limit. Okay, so here at A, we're obeying Hooke's law. Okay, we're obeying Hooke's law until it reaches B, where B is the elastic limit. خلاص, this is the limit over here. At B is the limit, because after B خلاص it changed the direction. So B is the limit. بعدين C is the permanent extension. Why is it the permanent extension? Because خلاص هون it's permanent, it can't go back because we broke the string. Over here خلاص you can't go back. Then D شو اسمه is whoa, wait. Plastic behavior. Yeah, this says, oh, what did I do now? Whoa. مهم. D is how did I do this? Plastic behavior. When you say plastic behavior, معناتها after the force became, يعني after خلاص you remove the force, it doesn't go back to the normal structure it is. An example of this can be, you guys know the pen caps, the caps of the pens. When you like, let me show you. 1 second. Like over here in the pen cap. Uh, what am I doing? Okay, مهم. Let me make this bigger. Okay. This pen cap, you know, when you bend this over here, خلاص, you bend it, it goes back to normal, right? Until if you keep bending it at a force, it's gonna snap, right? It's not snap, but it's gonna it's tiny. It's gonna خلاص, it won't go back to its original shape. So the cap is gonna look, see, this is the cap. It's gonna look something like this now, right? Because it's not going back to the original shape. What my point is, after it can't go back to its original shape, that's what we call the plastic behavior. Okay, so نحن قلنا A is obeying Hooke's law because it's straight. B is the elastic limit. C is the permanent extension. This is the permanent extension because can't go back. Then D, after the force decreases, that's what we call plastic behavior. Plastic behavior is when the force decreases and خلاص, it doesn't stop. Here the force is still increasing at C. Okay, the force is still increasing. You see stretching force, it's still going to the right. So once it goes back to the left, once the force starts decreasing again. Question 8. Apply Hooke's law. Okay, F equals K delta I is the same as what I told you. Remember, K equals F over delta I, ish I as the L, delta L. Whoa, 1 second. So I said K equals F over delta L. Um, what's it called? It's the same as saying F because if you cross multiply, it's the same as saying F equals K delta L. Okay, so this is the same thing. It's known as Hooke's law, Hooke with an E, yeah. So then they ask you if the force is 50 newtons, the elastic limit elongates by 25. So they gave you delta L is 25 centimeters. Okay, find the spring constant. We said the spring constant is K equals F over delta L, so 50 over 25. But this is centimeters. We have to make this to meters. So what do? We divide by 100. So you take it back 2 from 0.25, and then you divide this, you get 200. Okay. Okay, underline the quantity that can be measured by a spring balance. A spring balance, for those of you who don't know how it looks like, uh, it's this here, over here. So this is actually a spring. You hang something, and what do you measure? You measure the force, right? You measure the force. This is actually, see how it says newtons? That's the force. Question 10. Okay. Uh, when you're relating force with extension, or extension, you could say elongation actually. We said this is Hooke's law, right? Hooke's law. And then he said, what's the spring constant? K. And what do you want? K. K equals F over delta L. Okay. K equals the force. Let's take the first one, 2 divided by, this is 8 millimeters. Okay, 8 millimeters. So we have to make it into meters. How do we do that? Millimeters to meters, you divide by 1000. Okay, so it's going to be 2 over 0 0.123. Okay, here 0.008 meters. You divide this and you're going to get 250 newtons per meter. Okay, question 11. Okay, this one's a bit tricky one. Okay, most people didn't understand this when I explained it in school. Um, a student is making a spring balance. Okay, if you want a spring balance, like look here, you have the spring at the top, it starts going down, right? This over here at the top, the red line, if you can see it. Okay, to make a spring balance, you have to have some sort of measurement system, right? Like you see these 1, 2, 3, 4, 5, 6, whatever. You have to have some sort of measurement system. So this student is making a spring balance using a spring with an arrow and an ordinary ruler over here. Okay, she wants the existing marks on the ruler to correspond to the force applied to the spring balance in newtons. The ruler is in centimeters. Okay, what do they mean when they say correspond? Oh, what did that do now? Wow, hold up. Question 11. Okay, when they say correspond, okay, it means directly the same thing. So at 0, it should be 0 newtons. At 1, it should be 1 newton. At 2, it should be 2 newtons. That's what they mean by corresponding. Let's look over here. We want to find the spring constant. K equals force over delta L. Okay, K equals, you can take anyone. We know that since we want it to correspond, that means at 1 centimeter, it's going to be 1 newton. Or if you want at 2 centimeters, it's going to be 2 newtons. And 3 centimeters, it will be 3 newtons. And 4 centimeters, 4 newtons, and so on and so forth. So you can take any one, and you'll get the same answer. But I'm going to take, to make things easier, I'll work with the ones. 1 centimeter and 1 newton. What's the force? 1. What's the delta L? 1 centimeter. How do we change this to meters? It will be 1 divided by 100, which is 0.01. And once you divide this, you get 100. Okay? A 60-kilogram diver is free falling in mid-air. After a certain time, he reaches a constant speed. What is the term to represent the speed that the skydiver reached? Okay, and I told you, once you're falling in air or speeding up or whatever, you're gonna reach a velocity that's constant. And what do we call this velocity? I told you is the VT, which is the terminal velocity. And what's the net force acting on the skydiver once he reaches that speed? It's 0 newtons. I told you to reach the terminal velocity, to have the constant terminal velocity, you need to have a net force of 0 newtons. Okay, what is the magnitude of air resistance at that moment of time? Okay, to have a 0 newtons to have a 0 newton net force, let's say this is the person, he's skydiving. Okay, okay, he's skydiving, right? Okay, he's falling down in the air, right? So what force is going to be acting here? It's going to be the weight, obviously. And how do we find weight? Let's just say weight. Okay, and since we have a net force that's 0, that means there's going to be a force canceling out the weight. And in this case, obviously, like we said, it's going to be air resistance. So let's call it R. Okay, since R is canceling out the weight, that means R will be equal to the weight. So if you can find the weight, you can find the R. How can we find the weight? W equals mg, W equals the mass, which is 60, times g, which is 10, and you get 600. So the weight is 600 newtons, and the air resistance as well would be 600 newtons. Okay. Question 13. David has a spring that's unstretched at 5 centimeters. Once he hangs the weight of 20 newtons, it becomes 15 centimeters. What's the K spring constant? K equals the force over delta L. Okay, so K equals the force, which is 20, over delta L, which is final minus initial, so 15 minus 5 centimeters. Okay, you get 20 over 10 centimeters. We need to make this into meters, so we divide 10 by 100, which is 0.1, so you get 200 newtons per meter. Okay, question 14. This one's you memorize them. Strength is how strong something is. So if it has strength, that needs a large force to break it. Stiffness means yani it can stretch. Okay, like a wood is stiff because you can't really stretch wood. Elasticity means it goes back to the original size and shape after pulling it. So like a string would be elastic. The coil, remember the springs, these would be elastic. Plasticity means it doesn't go back. Okay, that means it stays deformed after a pulling force. Ductility means you can change it into wires. Okay, if something's ductile, you can make it into wires. And brittle means you can break it very easily. Okay, after the elastic limit. That's it for today for the physics AMS. Good luck, everyone. If you have any question, you have my phone number. I will post in the comments. Thank you so much for watching. Good luck.